So let's look at some data. So here's some data of a fellow named Brendan Frey. He took a bunch of pictures of his face and a film. And he started making faces. So it's data, it's framed around his face, and he's making faces and taking pictures of himself. And then transferring that into a whole bunch of images, so each frame of the movie. And so in any particular frame, you've got his face, and it's arranged in an array. And we have about 2,000 of these images, 2,000 frames. Okay? Every face is a point in a high dimensional space. Every frame is a point in a high dimensional space. Okay? The question is, what is the dimensionality? Well, a really easy and dumb way of thinking about this is to think about the array itself, but string it out. Take one column and attach the next column at the bottom of that, the third column at the bottom of that, fourth column at the bottom of that. Take every column in that frame and add them one onto the other, so you've got one long column. That's a vector. The elements, what are the elements of the vector? The elements of the vector is going to be the value of that gray scale. It's going to go from 0 to 1. 0 is light, 1 is black, or vice versa, right? So it's going to go some measure of the grayness. So every one of these guys is a vector in some high dimensional space. So we have 28 rows and 20 columns. So the arithmetic tells me that's a point in a 560 dimensional space. Okay? So what am I doing again? I'm going to take this column. It's going to have different values. That's close to 1. That's closer to 1. That's closer to 1. That's close to 0, etc. And then to the bottom of that, I'm going to attach the next column, its values, next column, etc. All 20 columns are going to be stacked on top of each other. So I have a single vector, 560 dimensions. Okay? Any questions? All right, so what are we going to do about this? So let's do this. F, R, nav. So I'm going to get this data. I'm going to scale it. Sorry, I'm just going to center it, not scale it. And get the singular value decompositions like I suggested. You can look at the scree plot itself. So if I'm looking at these are the ratios of the singular values to the largest singular value. So the first one is there, but then it drops off really quickly. So we've got 560 dimensions to play with, but a lot of the action is happening in low dimension. We might be able to get away with far fewer dimensions. Maybe these aren't so interesting. Alternatively, looking at the proportion of the effective dimension that we've got, we can get a far way up here, but 80% of it, with only 100 dimensions instead of 560. Okay? So the notion is that there's not a lot of dimensionality in this data. Maybe we can get away with fewer dimensions. And so I'm going to say looking at 30. Oh, let me just check that. Right, so here we go. Looks like I lied. I'm going to look at 20. So there's our data, at least a sample of them, I think. So there's a single point. And as I go through, I'll see bunches of different. So that's what our data looks like. Okay. Lots of data points. So here they are in 20 dimensions. I'm just going to make those points. And here's the navigation graph. So 20 choose 2 possible scatter plots to look at. And you see that, so in the first 2 principal directions here, principal axes, I've got, some kind of structure here, some grouping up here, density there, and some trailing things off here. And I could take any one of these, just scale it to the selected group, and show you the faces. So that they look kind of alike. 560 dimensional data down to 2 dimensions. These guys that seem to be neighbors in the same part of space, this kind of frowny face, that's reassuring, right? Remember, we don't know we're looking at faces. We don't know anything about this. Just strung this out in a really dumb way and said it's a vector of 560 dimensional space. Is there a lower dimensional space? This is the direction, these are the 2 directions that are occupying the greatest variation in the data. And we lay them out according to this new y1 and y2 coordinate system and look at different parts. And because they're faces, we have a sense of whether or not it makes sense. So there's Happy Brendan. Right, so those guys again look kind of similar. So it seems to be doing a pretty good job. So we had this 20 choose 2 possible pairs of scatter plots. You have to see this really big to see that there actually are edges there and pairs of variates. So as before, we can navigate around through that now 20 dimensional as opposed to 560 dimensional space and see what's happening there. And you recall last time, it looks like the principal components, I'll pick, I think, different areas than I did last time, look kind of like they're capturing images that are alike if they're near neighbors just in this first 2 principal components. Okay. Any questions on that? That's where we left off last day pretty much. And I'll revert these back to those guys. So we could explore this as we did any other high dimensional set. Looking around at the, let me just grab the node, at the structure in the data. And you see those points we select first are going to appear in different positions depending on the projection. So we're looking for interesting structure in the data as we did before. See, it sort of is this convex cloud here to a fair extent. If we go back, the first 2 actually was showing a little more variation in the density that you could see. And back there, whoa, that was interesting. So that little trail of guys in the middle here now. So I'm just going to play here to see what these guys look like. Set the faces. All right. So mainly this kind of pouty face that's in here, mixed in with some smiling. Everybody can see those? All right, so you got 20-dimensional data. That's 20-dimensional data like any other 20-dimensional data set. We could, in fact, run the scagnostics on it like we did before. So here's now the scatter plot that's reflecting this group. Let's make these linked. Select all of these, put them back to the circles, and scale to the world, and all the same size. And I'll just have this participate in that group. All right, so they're linked now. Okay, so looking at the scagnostics, we have this pairs plot. We now have 20 choose 2 pairs. And see what seems to be interesting. And it looks like there's a bunch of sparse points up here. Sparse but very little outlying. Ones that are clumpy, the clumpiest points are maybe these. So we can investigate this as we did before and see why we're picking up. These are going to be the scatter plots that have the highest amount of clustering showing up by this measure. You can see the various densities there. And those are appearing curiously not in, so you get different pairs of principal components. I have the 1st and the 17th here, the 1st and the 6th, the 1st and the 4th, the 6th and the 17th, the 3rd and the 19th, the 14th and 16th, all picking up highest on this clumpiness. So again, trying to see what's going on in these guys. Just selected, see whether this is making any sense. Right, so that's a little clump that is identified there in that one display. And there, he's all sort of pursing his lips there. These guys are a little farther away. He's just on his way to pursing his lips. Okay, let's get more of these guys. So you see how that happens. Selected. No, I don't want these guys. I just want those ones. Selected and put them on a grid. So that's a little cluster that we find in the data set, largely on the 1st and 6th principal component. Okay, so great for exploring the data, seeing what's happening. All the tools that you had beforehand can be used after you've done a dimensionality reduction. Everything we did before was with the original variates, but it need not be. Okay. You guys get this at the back? Are those my slides you're looking at? No, huh? Didn't think so. So you can look at any of these scagnostics, looking for the particular structure. So this group here is got low on skewed, high on sparsity, low on outlyingness, and it's again all world circles, and you've got many, many more pairs of scatter plots being involved. So starting with V1, V7, V1, V5, V1 appears in a lot of places here, 15. So the first 4 are appearing pretty much anywhere here. So not so many outliers. Again, you see the densities here. And you might look at what are the characteristics that those faces have in common. Whoops, in those projections. Okay. So that was just doing this with scagnostic 2D on the reduced data set, the 20-dimensional data. So some remarks. So you notice that our dimension reduction, our principal component analysis here, made no use of anything peculiar to this data set, right? It didn't notice that there were faces. We didn't go looking for eyeballs and noses and things like that. And we didn't even care where in the pixel array the images, the components were. We could have mixed them up any old way. We'd still end up in the same place. So we're not making any use of any of that information. And even so, with this 20-dimensional reduction, we end up identifying points that are near each other in that high-dimensional space. Okay? So the principal components doesn't care which position we moved our array pixels into, as long as the same array position got moved to the same coordinate of the vector. Doesn't really matter. And we still get some useful positioning, even if we're only looking at the first two principal components. And what's really interesting, given we have tools for looking at high dimensional data, although relatively low, 20, 30, 40, 50 dimensions, not 560, we don't have to restrict ourselves to only looking at 2 or 3 dimensions, which is what you will often see people do, just looking at the first few principal components. We can reduce to 20 or 30, whatever that scree plot is suggesting. Get that down and still find some interesting features. What we're going to be restricted by is, of course, computational feasibility, because we'd like to be able to determine using scagnostics what are the interesting projections. So last thing is that principal components, you recall, is looking at linear subspaces. So we've already centered the data, they're through the origin, so we're looking at are the points near a subspace through the origin? All subspaces are going through the origin. Are they near that subspace? Are they close to a linear subspace of the original data? So the focus is on that word linear. Okay. Another fancy word that you might know of is these are linear manifolds. So manifolds are sort of, think of this as the subspace, but a manifold could be relocated. So a plane is a linear manifold that need not go through the origin. A subspace will go through the origin, but we can move or offset it to have it go somewhere else. That'll be a linear manifold. Okay, so another fancy word. So that's it for principal components.